Yes, I'm Boram Park from Ajou University, and I'd like to thank Professor Sang-Irang for inviting me. And today I'm going to talk about some preset problem of integers. It's based on joint work with Ilkyoo, who is a professor at Ajou University of Foreign Studies, and Dr. Ringi, who is maybe a member of IBS. Anyway, so actually, I'm graph theorist. This is not my main research topic, but Dr. Hong Liu, who got good news recently, visited my university about a year ago, and he introduced this topic to us. So I'm going to present some work related to it. So rather than focusing on specific research topics, statements, I will present some main research stream of this area or summary of the history. So please be relaxed. No difficult mathematics at all. Okay, so I will start with the most general question. General questions. So if you meet some combinatorial objects or set of combinatorial objects, then if you want to find some substructure OO prime with some certain property, then there are two fundamental questions. Maybe people want to know what is the maximum or minimum value of such O prime. Or people may want to know how many counting problem, how many such O exist, or how does it look like, was fundamental questions. So I'm gonna focusing on those two fundamental questions in some free set problem of integers. So I should give you the definition. So let A subset of on any abelian group, and a subset S of A is called a sum free if there is no x, y, z in S with x plus y equals z. So yes, actually if it's sum free, x, y, z do not need to be distinct. And this notion formally defined in 1960 by Schur. So people called such x, y, z is called Schur triple. So okay, so I'm wasting the blackboard. So okay, so my concern as my title is I want to know when my group is integer group with user addition is my group, and A is a square bracket of n, what is a set of integers from 1 to up to n. Several facts we know. There are several facts we know. Maybe first exercise would be, I forgot to denote, yes. So I denote by mu A is going to be the maximum size of some free set in A. So as long as A is finite. So first exercise, it is equal to n over 2 ceiling. Does anyone who know the extreme example? Yes. What is it? Yes. Pause. And the another, maybe one more. Right. If you just collect all integers greater than n over 2 of floor, then it is also some free set, and there are only two extreme examples actually. So people also studied about the structures of some presets. As long as you know, there are 3 papers about the structures. What the structure means, the first paper is by Freeman in 1992. his statement is like, if your sum-free set is large enough, maybe this number, maybe. Yeah, if your sum-free set is large enough, then your sum-free set is a subset of this or this. Somebody called this kind of stability result. And after that, that's the Howells, Freeman, Sauce, Temkin, and they also give some result. If your S is large enough, lower than this number, 2 and 5 minus some constant or something, then your sum-free set is this or this or this or this. They give 5 possibilities. And most recently, he uploaded a paper in 2017. He also gives some statement, of course, lower than this number. So if your sum-free set is maybe minus some, yes, then your sum-free set satisfies this. So actually, those results actually first two, maybe from the conjectures by Ajou and Cameron, because Ajou Cameron asked about the number of all sum-free sets. So Ajou Cameron conjectured that this is going to be n over 2, big O of n over 2. It was conjectured by Radhas and Cameron in 1990, but it's settled by, now it's true, by Green. He proved it 2004, and Safuzi Henko 2003, they proved this independently. It was a conjecture by Cameron and Radhas. And also, there is another conjecture by Radhas and Cameron. They are asking about maximal sum-free sets. It's a 2 to the 1 over 4 plus a small o1 to n. It was also conjecture, but now it's true by Balo and Hong Liu and Chapriste and Charizade and oh, sorry. Okay, so I don't know. Trigalone, yes. Yeah. It was now published maybe. They uploaded paper in 2014 or something, maybe published now. I don't know exact year. Yes, anyway, now it's true. Okay. So this is a result when A is just the set of integers, when A is just a set of integers from 1 to n. Of course, you can think about any subset, finite subset of natural numbers or integers. There are a bunch of results about it, or you may think about another abelian group. But anyway, in this talk, as my title, I want to focus on this type of set. Okay, so there are a bunch of generalization or variations of this topic. So I want to explain a few of them, which might be really famous. Solution-free set. So first notion, which is generalization of sum-free set. As you may think solution-free, yes, that is the definition. So let L be a linear equation, say AK, XK is equal to B, where A1 to AK, B are all integers. And let A be a subset of integer. And we say S is L-free or L solution-free if S has no solution to L. There are no x1, xk in S satisfying L. So this notion formally defined in 1993 in Luza. Yeah, sum-free set is an example of solution-free set. By set your linear equation to x plus y equals z. So maybe examples. So anyone can see something here? really not important at all. Anyway, so sum free is the example. So by set your equations x plus y equals z, or Seddon set, it's also a famous set in extrema set theory. It's maybe x plus y equals z plus w. It's a sum-free set with this equation, or progression-free. Also, x plus y equal 2z. Sum-free set, L-free set, u, etc. So, actually, he defined the notion in 1993. People already studied this notion in various names in the history. Okay, so I will denote by, I will denote here, mu LA is the maximum size of my L-free sets, of an L-free set in A, mu LA. Okay, so yeah, if you're focusing on this problem with this integer set, okay, so not. So in the another story, if you are focusing on some noise. If you result on when A is square bracket n. And actually green, so one theorem by Green in the 2004, he proved that if L is linear equation, linear homogeneous equation, homogeneous means the B is equal to 0, then number of L-free sets in square bracket of n is equal to 2 to the mu of L square bracket of n plus literal n. He proved this result. But yes, it's really quite nice because it's connecting about the maximum size of some free set and number of some L-free sets. But the problem is it's quite hard to know what it is. So if I summary all the equations people studied till now, the equations people studied is, of course, maybe the trivial, some free set or some Seddon set, and progression free set, but for general K, and x equal y plus kz, or px plus py equal qz, or maybe better to say rz, and the px plus qy plus rz, and maybe x plus y plus, oh, it's better to say x2, xk equal x. Yeah. These are all the equations people studied. So if you found some nice result about the maximum size other than this equation, it's going to be new result. Okay. Yes. And this one, so maybe 4 papers. If a k is equal to, it's a progression free set. It's the old classical result. And if a k is equal to 3, it's the result in 1996. And for the other case, so there are 2 papers in 2000 and 2004, something. And there are only 1 paper is about this in 2003, and Ruzag and Schoen, yes. And for the other papers, actually, they only give some partial result, actually. Partial result and partial result. And all the papers talking about all the equations, they try to find maximum size, or they try to describe structures, or they try to count maximal L-free sets of these equations. Yes, some are maybe partial, and some are quite solved completely. So definitely those are partial, because they are quite new results, like a 2017 or 2007 something. Yes. Okay. So anyway, even though you're focusing on square bracket of n, the problem is difficult. Yes. So mathematicians, if you make a difficult problem, then you make it more difficult, right? So in 2005, Cameron suggested this problem to think about this problem in a higher dimension. So maybe higher dimension. Okay, so something wrong with my mic. Yes, maybe. It's my problem anyway. Their problem? I don't know. 모르겠어요. 저도 잘. 어떻게 해야 되죠? 그냥 마이크 할까요? 어떻게 되죠?
아니야, 배터리 많이 있는 것 같아.
네. 다시 한번. 네. 아까 여기에서 그런가? 자꾸 움직여서. 네. So people thinking about higher dimensional case. So it started by more loud noise. He does not want to listen my talk. It's better. Yes. Yes. And Cameron suggested think about higher dimensional case. What it means, so he's thinking about maybe actually free set, L free set, in d-dimensional lattice. So integer lattice. Yes. So he suggested this problem in the problem session of British Combinatorics Conference in 2005. So it was 2005, and he also uploaded a small manuscript, unpublished manuscript about the observation of some L3 sets in some free sets in d-dimensional lattice. At the time, he conjectured that for every d, there is some real number kd such that so this notation is for the maximum density. It's nothing but all number of balls the size. It's taking about yes. Yes, I denote the nu for the maximal density. He showed that he conjectured that for every d, there should be a linear number d, such that maximum density is equal to kd plus big O over 1 over n. He's conjectured and still open. And he also conjectured that this number should be 1.6 if d is equal to. He also conjectured. And after his conjecture, there are a few partial results about it. And a few years ago, the two-dimensional case was solved. Two-dimensional case is solved. So it's about Ajou and Boram in 2017. They solved, solved conjectures when d is equal to. Yes, extreme example to think about is a d-dimensional lattice. It's extreme example is the points between two parallel lines, and this is x plus y equal 1.6n. The other is x plus y equal 8.8n. If you think about all the points between two parallel lines, then it is going to be some free set in two-dimensional lattice. It is an example suggested by Cameron, and they settled the conjecture about the d is equal to. The proof, yes, they consider many cases in the proof, but each case they are using only one simple observation. What it is, so if you agreed, suppose that some point is in your sum free set. Suppose that your point is in some free set, then if you're thinking about, so I would say this is a, this is a vector n, n is n. Then if you're thinking about some vector, maybe thinking about n minus x here, then half of this red rectangle cannot be in S. So in other words, at most half of this red rectangle are in S. Because if you're thinking about some member y here, and if you are thinking the points which is symmetric with the center, say z, then if you sum up with x, y plus z plus x plus, yes, it's x plus y must be z. Yes, right? Am I right? Yes. Yes. So because here x plus, yes, y. Oh, am I right? Oh, no. I was confusing. So just thinking about x, right? Just x. Yes. I was confusing about my problem. Okay. So he used this idea repeatedly. It's a really basic idea, isn't it? So he just used this basic idea repeatedly to just beat the conjecture. And of course, there are many cases in the paper. So actually, this paper is a strong motivation to our research problem. So before moving on my specific research question, I want to give you another major research stream of this area. So I will title like a partition. I don't know if it's a really right name. Partition into L free sets. So this may not closely related to my research problem, but this is also one of the mainstream of this area. So I will quickly mention about it. So there are two classical papers about this problem, and by Schur and Radhas. And Radhas' PhD advisor was Schur, and this is his PhD thesis paper. So maybe their work. Anyway, so there are two classical papers related to that. So I think it's also a really major stream in this direction of research. So partition, like looking like a coloring. So in this paper, he conjectured something we call the Radhas boundedness conjecture. So yes, if I state quickly about it, so if your L is a linear homogeneous equation, then with n variables, then there is some integer fn. such that satisfying this. Yes, what it means. So every Fn coloring of natural number, for any coloring for natural number, if there is a monochromatic solution to L, then every finite coloring of N, there are monochromatic solution to L. That's Radhas boundedness conjecture. Actually, the first shape of this conjecture may be a little bit more complicated. But anyway, people work on this conjecture more and more. Now people know this is equivalent to the Radhas original conjecture. So yes, it's a really, really open. And the case where N is equal to 3 was solved is in 2006 in Jacob Fox and Kleitman. Yes, for the other cases, yes, it's really open. Yeah. And another mainstream, it's also related to this Radhas problem. So actually, in the paper, she showed that here this means maximum integer m, such that your m can be decomposed into n some resets. So yes, he defined this notion and he showed that it's of course that there are several papers studied this value more, but because of this type of statements, people also thinking about GLN, and that you may thinking about L free sets instead of some free sets. So the main question here is maybe existence of such a number if you generalize some L. So people called it Ramsey type theorem, Ramsey type problem on algebraic equations. Yes. So what it means, like this number exists. Does it exist? Is the question. So if you specify some algebraic equation L, and if you specify some number, so people ask about is this number exist? So in other words, if you just affix some algebraic equation, and you want to know any finite coloring of natural numbers, can you find monochromatic solution or not? So for example, people know that, of course it's a one paper, people know that it's too low. Yeah. This does not exist. This does not exist if it's a 16, and if L is x plus y equals z squared. It's also a paper in 2002. So people keep asking about this question. And as long as I'm aware, Hong Liu, who got the good news recently, visited IBS a few months ago. He also gave a talk about this problem. Yes, so at that time, his research paper is talking about not exactly Ramsey type problem, but he wants to count the number of monochromatic solutions of some finite coloring of natural numbers by setting your algebraic equations, some kind of algebraic equations. So I think this type of research in this stream is also a major line of this research. So as you remember the sum free set, definition of sum free set, so you can think about this problem in more general setting, algebraic other structure or some other type of natural numbers, infinite version, in many, many ways. So our research problem as one tiny research is about related to high dimensional case. So let me explain the problem and the statements. So now maybe section 2. So our problem is thinking about L free set in the dimensional lattice when L is non-homogeneous case, So as I told you before, yes, so I'm focusing on this higher dimensional case in some setting. So, okay, maybe few notations I want to introduce. There are few notations. So if your vector B is some vector, 4 vector, I will denote by this one as the nothing but of the product of all the members over here. And I will denote by this one as nothing but the dimensional grid of size of this one. So, and also for simplicity, I will denote by mu, k, b, n, maybe. Yes, maybe some A. This is the mu L A, where L is x1 plus xk, maybe better to say, as equal to B. So I will call it, so K sum B free. So, yes, I want to thinking about this linear equation, non-homogeneous case. So just for simplicity, I will just use, instead of writing all the linear equation, I will denote by KBA. Yes, so KBA. And for its maximal density, I will use nu for maximal density. So the first note, if n is large, so if n is large, you have this one, k, b, n. KBN is equal to, so it's a really easy fact. Yes. So, yes, maybe. So if your n-dimensional box, suppose that your vector n is much bigger than your vector b here, then maximal K sum B free set always contain this area. Because no possibility to take some elements here to make some B, right? So this counts this red area. So if you're thinking about K sum B free set, then your problem is down to this problem. Right? So you want to avoid K sum B in the square bracket of a B, right? So the problem is down to what it is. So now, yes, this is our research problem. Yes, what it is. So So what it is. So first note, yes, this is our question. This is my question. So second note, if you're thinking about this problem in one-dimensional case, then it's really easy. One-dimensional case is, yes, easy. So that is, you want to avoid maybe I say better to say n in square bracket n. You want to avoid, right? So it's a number, as the answer is mu, I say k n, is going to be, it's better to say nu. Yes, it's easy to observe this one, because you can use induction on K. Yes, of course, we want to think about the case where K is at least 2. So induction on K, if a K is equal to, yes, it's really easy, because you want to avoid x1 plus x2 equal n, right? So so not great. So in the one, you want to avoid x plus y equal n. Then the 1 of 1 and n minus 1, you're gonna take one of them, right? You're gonna take 1 of 2 and n minus 2, etc. So it's a really easy problem, and you know it's a 1.5, right? So the other case is also induction, right? So take a minimum of element of your maximum sum free set S. So if the minimum is quite big, then you're done, right? So yes. If your minimum is greater than n over k, then you may definitely obtain the ratio. Otherwise, you're thinking about S prime, which is intersection of n minus m. Then point is that this is k minus 1 sum free, because already you know m is included in S. It's a member of S, right? So it is k minus 1 sum free set. So you just use the induction. Then you may obtain the bound. Yes. So the result that we have now is, okay. Okay, so the theorem having now by Choi and myself is for every k, if n is large means according to k, if it's quite large, then maximum density of integer grid is equal to 1 minus 2 over k squared of a big O plus 1. So this is yes, the result I'm having. So extreme example is going to be the x plus y equal, you're thinking about all the points above this line.
Just think about non-homogeneous.
Yes, non-homogeneous is the simplest one among the non-homogeneous case in two-dimensional case. Yes. So if you're thinking about this set, yes, it's an extreme example. So I just replace B with N. So maybe if I just solve this one, so I want to avoid I want to avoid this one in want to avoid, yes. I want to avoid this one in the square bracket. So one reason I use unify this and this is because of this observation, right? Because if it's so large, then it's every here in the red part should be included in the maximum sum free set, maximum L free set. So it is sufficient to thinking about when they are equal. So yes. Right. So maybe it's better to say, yeah, n vectors in two-dimensional case. So this is the result we are having now. And of course, there are several further questions. So actually, we did this work last spring. But we are waiting because we expect that we may obtain more fancy result, but we struggled with several months more, but yes, we decide just writing up, yes. So maybe, so if you are interested in, then yes, please solve one of them. Okay, so first maybe the one we are really want to looking for, maybe stability version. So if you remember one classical result by Freeman in sum free set, he showed that if your sum free set is large enough, then your sum free set should be a subset of the extrema ones. So we want to find such kind of statement. If my sum free set is large enough, I don't know how large, then your sum free set is a subset of this. We want to find, but we couldn't. So maybe I want to know, so can you find some number alpha in R that exists? So it's like if your sum free set is L free set in this version is alpha n, then S is a subset of this one. So can you find such a one? So we want to know this part, but still, yes, no progress. And of course, you may thinking about, because this is going to be the kind of first try to thinking about two-dimensional case and a non-homogeneous. So you may thinking about the more general L with by thinking about other coefficients other than 1, 1, 1, 1. You may thinking about other type of coefficients, more general L. Or also you may thinking about counting problems. Right. So you may remember the one result in sum free set of integers by Green. He gave a statement by connecting number of L free sets and maximum L free sets. So can you find such a thing in D-dimensional lattice? Also for the work? Yes. Yeah, something like that. Or you may thinking about Ramsey type things in lattice. So as long as I'm aware, nobody thinking about this problem in the D-dimensional lattice. Oh, yes. Basically, we use induction on K. Induction on K. Yes. The problem is the basis step was K is equal to 2 and 3. And actually, inductive step is really, really easy, just like this. Inductive step was really, really easy. But the basis step, K is equal to, is really fundamentally easy. And the most difficult case is this one. Actually, we solved this case first, and then we just observed that, oh, it's a really generalized to general K. So all the ideas, all the proofs are focusing on this case when K is equal to 3. Yes. So maybe for the work. Yes. Actually, in the remaining minutes, I prepare a few sentences to explain the proof. But I think it's not a good idea because I only have 5 minutes, so I think I should stop here. So thank you for listening.